Howdy, y'all. So how many of you have used a thumb drive? Okay, and the other half of you are lying. And I'd like to thank the neighbor who loaned me a laptop for trusting me to insert a thumb drive of my own into it. That shows true bravery on his part. So when you use a thumb drive in your operating system, let's say Linux without an auto mounter, right? You're using your thumb drive. What does it appear as to the operating system? As like an abstraction layer. It shows up as a block device. And then you can format it, and formatting it allows it to show up as more than one block device. So you'll have like dev SDA, and then dev SDA 1, 2, 3, and 4, that being the device as a whole, and then its partitions. And there are all sorts of anti-forensics tricks that you can do to the file system or to the way the directories are set up. For example, you can replace the file system table, the partition table, so that it looks like your partitions are smaller than they actually are. So if you delete a partition and then you bring it back, you'll prevent it from it being seen by the operating system, but everything is still there and it can still be recovered. And in the past, people have played around with this. They've done, oh, piece of shit. If anyone has a Mac power adapter and would rush to the stage, I'd appreciate that. Tran, come on up. Okay, so in this case, you would still sort of be stuck with this abstraction layer that the thing is a block device. So even though, say, /dev/SDA4 would be missing, you would still find those same files in /dev/SDA. And you're kind of stuck with it. So what can you do to get around this? Well, Colin Mulliner did a presentation over the summer at Woot in which he took a Nokia N900 and he made it act as a disk for his Samsung television. And as he has this disk running, he installs a plugin. And the operating system knows that it shouldn't take dangerous plugins to be installed, even though it supports them internally. So there's a shell script which checks. The first time it reads the plugin, it says, is this a .swf file, which is safe, or is this a .so file, which is not safe? And if it's an SO file, it refuses to install it. And the way that Colin's exploit works is that the first time this file is read, it's a .swf. And the second time it's read, it's a .so. So when the operating system on the TV checks to make sure that the file is safe, it is safe. And then when it installs it, it's not safe. And this is how he jailbreaks the TV. So what more can you do in this style? Well, to do that, I figured it would be necessary to understand how the hell a thumb drive works, how the hell a disk works. Because if you just patch the higher layer implementation that already exists, you don't really see what's going on underneath the hood. So I went through and I began to make exploits for USB devices through the Face Dancer project, which I debuted at Recon in July. And the Face Dancer is a USB peripheral that lets you emulate a USB peripheral. So it has two USB plugs on it. One of them runs to your laptop. One of them runs to any other host. And then you write your USB device in Python on your workstation. And it appears to be real as far as the second machine is concerned. And this lets you do all sorts of fun things, because you can fuzz device drivers on the host. And like, if you consider that Linux supports every USB device ever manufactured except for the wireless card in your laptop, those are all open ports speaking complicated protocols. Imagine nmapping a host and seeing 1,000 open ports. You know, you would know that there's something somewhere in there that can be attacked. It's just a matter of figuring out what's easiest to go after. So having that tool, I wrote a thumb drive. And we sort of pigeonhole different things, and we get stuck with thinking of them as, you know, only having a particular purpose. And for years, I've been saying that I would never do a defensive talk because defense is just about making stupid graphs. But here, I'm having the disk defend itself against the host. Okay, so the idea is that I'm using the face dancer to come up with the behaviors that I can patch into the firmware of a disk, so that when that disk is forensically analyzed, it will destroy itself. And by doing this, you can then make a disk that defends itself against the attacker in a forensic environment. And whenever you're in a forensics lab, you've got lots of rules that need to be followed. So instead of having, a list of best practices or behaviors, they have an actual script. Take the thumb drive, stick it in the machine, push the button. And by that point, you can already have the evidence gone. I'll be showing you how to do this in a minute. I'd like to thank Sergey Bratis and the students from Dartmouth, with whom I did a lot of the prior research on USB hacking and the packet-in-packet research. Also, Colin Mulliner for making his time of check to time of use attack for the Nokia N900. You should read his paper from Woot. And I have upcoming hard disk research, which unfortunately I can't yet present, but will be presenting with friends of mine from Eurocom and ECH in Zurich. When that comes out, you really ought to read it. It's going to be very good. So you think of this disk as a block device, but it's actually a computer that's talking to yours over a network. This network is called a bus, but it's really just a network. You have packets that go across. It looks a lot like HTTP, or maybe more like TFTP, but it's still just a protocol. And you can exploit this protocol, and you can fingerprint this protocol, and you can port scan this protocol, and you can do all of the stack evil things that you would do in the 90s. All of those still work today for USB. But in the past, it's been too difficult to get development tools into the right position to begin attacking it. And now we can do all of these things. We can emulate any USB device that we like. You can make a fake thumb drive. You can make a fake iPhone. You can run a jailbreak on a fake iPhone. You can do all of that fun stuff and see the actual packets go across, and then come up with your own behaviors and your own nifty tricks like that. So please read the fucking papers. I spent a lot of time writing these things, and they're meant to be read. And also read Colin's paper, the Read It Twice paper from Woot. There's an anti-forensics paper by the Grug, and some nifty presentations by Nt80 from Dual Core. And they take different views of this. So the Grug assumes that you have remote access to a server. You have placed files on the disk that you need to have in order to accomplish your evil mission. I know that I'm stereotyping here, but with the Grug we can assume it's an evil mission. What can you do in order to make file system forensics tools not notice this? So he does things like marking a region as damaged, and then the forensics tool will skip over it just like the real file system would. Or he noticed a bug in one of the forensics tools where inode 0 would never be looked at because it started searching with 1. Now, Nt80 took a different view of it. He assumed that your disk was being read by a criminal forensics lab after it had been seized by the police. Things work differently in the States for that. The police need warrants and all sorts of things that are different from here. But it still goes in, it still gets examined. So what can you put on the disk that makes it particularly annoying to grab? Well, for one thing, the forensic investigator is expected to make an image of RAM if he's able to. Okay, so for that, the disk gets rebooted into, say, a cold boot program that dumps an image of the RAM. Well, if you can make it so that it won't boot from the thumb drive, but actually boots from the disk, recognizes that a thumb drive is in, and then nukes the rest of the disk, you can sort of destroy the evidence as it's being captured. But he was limited by not being able to control the disk itself. So there were behaviors that he would have liked to have done to destroy evidence that he wasn't able to do in that framework. And today we'll be discussing those sorts of behaviors. What you can do if you control the disk and if the disk actively collaborates with you and against a criminal forensics investigator. And this takes advantage of particularly obvious and easy to fingerprint behaviors of that investigator. This is the prototype of my hardware. It's called the Face Dancer. I've just now gotten prototypes of the Face Dancer 20, and I have almost 100 left of the Face Dancer 11, which I've been passing out at this conference. The idea is that the board is a network adapter. So you can hop onto the Magic School Bus, and you can start playing around and emulating a USB device. This began when I was teaching an operating systems class for Sergey Bratis, and I was describing the different internal buses, and he started jumping up and down and screaming, "It's not a bus, it's a network. Stop using that word." I have an open award of $100 to anyone who can teach Sergey how to dance Gangnam Style. I need video evidence. So the Face Dancer project is a USB device that emulates a USB device. And it allows you to write your USB device in userland Python on your own workstation. You have access to the gigabytes of RAM that your workstation has. You have access to whatever terabytes of storage you might have. You can access the internet. Your script can do anything that it would regularly do on your PC because it really is running on your PC. All the board does is ferry USB packets back and forth to the victim host. And this is used as a development tool, not as a deployment tool. The idea is that when you're writing your exploit, you have a debugger hooked into, say, the victim software. Okay, now in the field, you can never have a debugger, right? But you use that in order to get your memory corruption exploit to work. In the same way, when you're writing a USB exploit, you need tools to make it less painful to do the development. And that's what this tool is for. So it allows you to rapidly write an emulator for whatever you like, and then you can start prototyping behavioral changes. And later, after you're done, you can take any USB development tool and move your behavior into it. So Atmel and Texas Instruments and all of the different chip vendors will give you pre-written USB mass storage stacks for their chips. But they're held to development for because you've got to compile your code and then reflash it, and if it doesn't work, you've got to reflash it again, and you have very limited debugging access. Here, you use the Face Dancer to first develop your behavior or your exploit, and then only after it's finished do you move it into the target device. This was released at Recon in 2012, and then at Breakpoint in Melbourne a few months ago, I released a device firmware update emulator for it. So you can actually catch firmware updates intended for devices. So whenever you have a device that can have its firmware updated, you can have the GoodFET or the Face Dancer emulate this, and then it can catch that firmware update, and then you not only have an image that you can begin to reverse engineer, but you also know how to replay it to flash it into the target device. And while they do use checksumming, there's almost never any cryptographic verification until you get to very high-profile consumer devices. So if it's less complicated than a cell phone, you can usually just write anything you want over the firmware. And here I'll be presenting mass storage emulation for the same platform. This is how the modern Face Dancer works. It's about the size of a thumb drive. It has 2 USB device connectors. The upcoming model adds USB host, which I thought was unnecessary, but it turns out it's very handy. And this is all that the architecture is. You have just an FTDI chip, the same as you would have in an outdated Arduino. This connects to an MSP430, and then the MSP430 connects you to a MAX3420, which is a USB device controller. Or in the upcoming model, we use a 3421, which can also do host. And then the Python client software just sort of shuffles packets over the FTDI chip into the MSP430, which takes care of handling the 3420 chip. This is the MAX3420. It's a minimal USB device controller. Its only purpose is to adapt from USB to SPI, which is a more common embedded bus. And as soon as you start fuzzing device protocols, you get crashes everywhere. It's great. You can also pick really rare or outdated products because the Linux kernel or any other kernel can't tell the difference between you and the real device. So if I say that I'm a Lego Mindstorms infrared adapter from 1998, the kernel will still load the appropriate driver and allow me to communicate with it. And if that driver was written by a 16-year-old as he was first learning to do kernel development, then the odds of a memory corruption exploit are pretty good. And also, unlike other regions in the kernel which get cleaned up by the developers whenever there's a crash, well, how many kernel developers have a Lego Mindstorms infrared adapter from 1998 and use it daily and care enough about it to debug the driver if it crashes? Yeah. So the boards that I have here are just the PCB and they're not yet soldered. I'll mail them to you from Tennessee for free or for low cost. So if you're a student, don't send me any money, just send me a shipping address. Send me a properly formatted shipping address. But you're going to get to experience a German customs party. So don't expect them in less than a month. And I have a few hundred here to give away. So in USB, the names of things are a little bit different. And I'm going to bounce back and forth between the networking terms for these and the USB terms for these, which will get confusing, and I apologize for that, but there's no way around it. There are these things called endpoints, which are the equivalent of ports, except that you have very few of them. So instead of it being a 16-bit field, it's a much shorter one. And usually they're in the low single digits. Endpoint 0, or port 0, is a special one. It's the setup endpoint. And this is used for configuring the device. This is also the only port that's bidirectional. Everything else is either input or output. The setup exchange is called enumeration. And this is how the host decides what driver to load for your USB device. Devices are described by descriptors which have nested lengths and structures which are unique to each device class. So these become difficult to parse, and quite often you can get crashes by just playing around with the nested length fields. Now the class types are standardized. So if you have a USB mouse or a USB disk, then it uses a single byte to describe what type of device it is. And that says, you know, I'm a keyboard or I'm a hard disk. The vendor ID and the product ID are ignored in this case. They only matter when you're emulating something that's vendor proprietary, such as the FTDI chip or a Wi-Fi adapter. We can emulate either because we control the descriptor. Now, there's some implicit assumptions that we all make about disks. We assume that blocks are read as they were written. On a modern disk, you probably won't even see a read error until it's too late. We also assume that the order in which you write these blocks or read these blocks doesn't matter. But that doesn't need to be true. And we, in general, just assume that it's just a block device. But all three of these assumptions are horseshit. Because the disk itself can send whatever it wants in response to that query. So if the host writes something to a given sector, when it reads it back, you can make it read back something different. You can erase things when you're not told to. You can swap out between different images. You can do any of these behaviors. You just need to know when to do it. So Colin Mulliner wrote this time of check to time of use exploit for the Samsung TV. And the exact rule, which I believe was encoded in a shell script, but he might correct me on that, is that if the plugin is a .swf file, then install the plugin. So what he does is he has two different versions of this XML file, and he swaps them out in the file system. So as soon as you finish reading it the first time, it replaces the first block with that of a different XML file. And by doing this, he can make it pass that check and then get installed as it's malicious. And this lets him inject a shared library that contains a telnet server. Now, in order to do that, he had to flush the file system cache, because the VFAT driver will hold all recently accessed files in RAM in order to avoid repeatedly thrashing the disk. And his way around that was that he noticed the machine had 256 megabytes of memory. So he made a 300 megabyte file by padding his 1 kilobyte file with 300 megabytes of white space. Now, as soon as he has it installed, he can then telnet through, and as he's finishing the jailbreak, he can remove this file. So it's not as if he's wasting space in the disk, and it's not as if this makes his jailbreak any less valuable. And again, he does it by sort of separating the clauses of the shell script inside of the device, and then changing things in between. Okay, so first it says, you know, if the plugin is an SWF, and at that point it is, well, then install it. And it's during the installation that he changes it. He did this on a Nokia N900 in disk mode. And this would not have worked without the ability to do active sectors, which is why it's so important to control your own disks. So let's build a disk. The first thing that you do when you start building a disk is that you grab the USB mass storage adapters. The mass storage file. The PDF file describing this standard. And you think, oh God, this is going to be difficult, and then you print it out and it's only 18 pages. And the reason why it's only 18 pages is that it just says, look to the SCSI standard, which I think is 1,900 pages, and I'm not sure that I've printed every volume on my friend's printer. I might owe him some toner. So the USB mass storage standard then just describes this wrapper. The idea is that you have a command block wrapper that comes first from the host, and then you have a command status that goes from the device back to the host, and in between you have the data. Now the host always speaks first, and the status of the device always comes at the end, after the data. So whereas in HTTP, if you request a file that's not there, you get a 404 error, and that's nice and short. In SCSI, if I request, say, a 650 megabyte file, all in one connection, and then the host or the device can't find it, or doesn't have those blocks, or there's a read error, it has to send me that many megabytes of garbage with a 404 error at the end. This is particularly annoying when your USB device emulator is slow and you have to avoid a timeout. Because if the host requests too many blocks, then you'll get a read error, but you can't tell it that you're unable to send that many blocks. You have to let it run all the way through and then time out. The way around this is horrifically disgusting. You have to give it your proper SCSI descriptor, but have an error at the end, and then it will request it a second time longer, just in case that works. And then in the longer one, you have a field that says, you know, I can only handle 100 blocks at a time. Now, the SCSI standard describes everything interesting. So we want to move on to the SCSI commands. In SCSI, your command verb is a single byte. And these are listed. The easiest listing to get through is actually the Wikipedia article, which for once is relevant and technically detailed and free of politics. Much better than the French SECAM article, which in Wikipedia is just 10 paragraphs of why American television standards are garbage, and then one sentence mentioning that the rest of Europe uses a standard that's kind of related. So these commands include like test unit ready, which just makes sure that your disk itself has finished loading all of its software and is ready to begin a conversation. Or inquiry, which is how you request the size of the disk. There are also some really antique and strange ones, like read format capacities. Do any of you remember when a floppy disk could be either low density or high density? Well, SCSI still supports that. So as you think of formatting a disk in modern times by overwriting the blocks of /dev/SDA, the SCSI standard thinks of formatting as actually doing a low-level format of every ring on the hard disk. And it's conceivable that a hard disk might allow the host to choose between different capacities in order to vary the reliability. In practice, disks don't ship with this feature, but you could easily implement it, and the support is already there. A1 is also rather fun. A1, which I believe is only used by the Linux kernel, says, SCSI is kind of ugly, wouldn't you rather speak ATA? Later on, we'll use that for an exploit. There's also the 28 and 2A commands, which are read and write sectors. But as I'll get to in a bit, it's not quite that simple, because this is a very old standard. And they kept having to increase the number of bits describing the block address. And they did this by making separate read and write commands. So there are 4 or 5 different read commands and 4 or 5 different write commands, any of which might or might not be supported by any given disk. There's also the 1E verb, which is prevent or allow removal. This is how you can make a CD-ROM drive refuse to eject the disk. And there are plenty more of these, some of which are documented and some of which are not. And they're spread around all sorts of different SCSI standards that describe specifically which SCSI physical connector and which revision of the SCSI standard you're talking to. But it's not quite clear exactly which of these you should be reading while doing a USB SCSI disk. So the driver authors don't know either, and they all have different feature sets. And you can use this to fingerprint the host to figure out if you're in the right one or a malicious one. There are also complicated structures involved in here. So it would be worth fuzzing this in order to get crashes in the host, or memory exposure vulnerabilities. With the SCSI library on Linux, if I tell, say, a scanner to give me a 1 megabyte image, and it can't provide that image, and it times out, remember, SCSI doesn't really understand a timeout. USB does, but SCSI does not. So the combination is that the kernel will allocate that buffer, and then after it's allocated that buffer, it will pass it to the userland client, but it won't populate it yet. So this gives you a leak of unpopulated memory that used to belong to other users, but doesn't get erased when it moves between users, as say malloc would do. And this ATA pass-through feature is an option, but it's not required. So almost every disk will just say, no, I don't want to speak ATA, I'm happy with SCSI. If you want to mess with SCSI directly, there's a set of utilities called SG3 utils. And this allows you to sort of bypass the operating system and speak to the disk as a disk using its own native commands. This is a lot easier to debug when you have bugs in your implementation, because when you're writing a disk from scratch and it doesn't work, the kernel demessage is not there to help you. All it will say is, this doesn't work. Or read error, disk not functioning. The error messages are absolutely useless. So what you do is you use the SG3 utils to run just the command that you think you've got wrong in verbose mode, and then its error message will tell you what you did wrong. So for example, you can use sginc to do the inquiry command, and then the reply that comes back will tell you where you messed up. There are also commands for doing low-level formats, for reading the logs of the disk, for resetting the disk, and for read and writing individual raw addresses, all of which might be useful to extract secrets from a disk. So what does it feel like to be a disk? No, I'm serious. Haven't you ever empathized with the disk? Don't you want to know what they're feeling? How their day is like? Well, if you think about it, during a normal day, the disk is there and it's getting commands from the host. And the host is saying, hello, how are you? How was your day? The usual questions that it doesn't really care about the answer to, but it asks anyways. And then after that, the disk is mounted. And the first thing that happens is that the file system runs through and indexes the beginning of the disk, because it assumes that you're always going to read the root directory. So it might as well already have that in cache. And then the user will request something from the disk, but not by its full path name, because the disk as a block device isn't supposed to know anything about path names. Instead, the driver will run through and crawl the directories, bouncing from one directory to the next, until it gets to the path that it actually cares about. So to read like /home/travis/.ssh/idrsa, what would happen is that first it would read the root directory, then /home, then /Travis, then /home/Travis/.ssh, and it has to do each of these in sequence because it needs to know where these blocks are to be found, and it needs to know them by block address, not by name. So that's a normal day in a disk. What would it feel like as a disk to be imaged? Well, it would feel like an interrogation, you know. What's at block 0? What's at block 1? What's at block 2? What's at block 3? What's at block 4? What's at block 5? But SCSI isn't exactly like that. SCSI allows you to specify how many blocks you want. So the host will actually say, give me the first 16 blocks, then the 32 blocks after that, then the 64 blocks after that, then the 128 blocks after that, and it keeps jumping up this size if you're using, say, the Linux dd command. And at some point it becomes too much for the disk and then it bounces down, but this is very different from how it feels to have a normal conversation as a disk. So these are very easy to distinguish and to fingerprint. So as these SCSI commands arrive over the bus with minimal wrapping, you can identify the host's dialect to figure out whether it's the right host. You can also figure out its intent. Because even though you're not supposed to understand your own file system, you can easily include a file system driver. Cameras do it all the time. So by figuring out the host's type of computer, what operating system it's running, what window manager, and after that, figuring out what it's intending to do to you as a disk, you can make the appropriate reply, which might be to erase yourself, or might be to show a Rick Astley video, or a Goatsy image. So you can do things like actively prevent the undelete bug, which is that, let's say that I give you my thumb drive to say give me a file, or if, at the end of this presentation I'll probably give my thumb drive to the angels to throw it up on the website. Okay, so when I do that, the angel that I give it to, he might think, you know, Travis is a good neighbor. He has lots of neighbors. Maybe one of them gave him some ODE on the thumb drive. And even though the file has been deleted, it's a FAT32 thumb drive. So deleting a file is just changing the first byte of the 8.3 file name to a 0. So that's easy to undo. So we could run through and he could grab all of my deleted files that are still there, and he could read them back. But if instead my thumb drive were smart enough to erase the file when it recognized that the file name were changing, then this bug wouldn't exist anymore. And it wouldn't damage any existing FAT32 driver, because in marking the file as deleted, you're also saying that you no longer care about it. You can do a trap on imaging to recognize when the host is trying to take a disk image of you. And through that trap, you can then erase yourself or change your image. So say that the particular forensics shop first takes a checksum of the disk to make sure that nothing is damaged in chain of custody. Well, if you had a block that just is a random block, and every time it's requested it gives something different, or a terribly simple trick. Every Windows machine, first thing that it does after it mounts the partition is it writes a timestamp. And the most strict rule of disk forensics as a criminal investigator is you are never allowed to write to the disk, because the defense attorney will say, hey, the government wrote to the disk. This doesn't count. Okay? So if the disk has two file systems and it only shows one of them after the timestamp has been written, then the disk imager will always get the first image. This also prevents you from leaking anything before the disk is imaged. There's another technique and tool that's available called a write blocker. And this write blocker just sort of acts as a USB firewall of SCSI commands. Okay, so with this write blocker going through, you never get the write command. So that timestamp is never written. And you can check for that. You can do host fingerprinting. So when I said that the first thing Windows does is write a timestamp, that's not quite true. The first thing that Windows does is it reads the master boot record 9 times. Are there any Windows kernel developers in the audience? So the way that caching works is that the file system does caching, not the block device. So if you have the command to read the master boot record 9 times, it will ask the disk 9 times. And the disk can give you 9 different answers. The reason why it's 9 times is the first time it runs through to see how many partitions exist. Then it wants to know the beginning of the first partition, and the end of the first partition, and the beginning of the second partition, and the end of the second partition, and the beginning of the third partition, and the end of the third partition, and the beginning of the fourth partition, and the end of the fourth partition. And at that point, it's ready to begin mounting these drives. So if you ever wanted to make partitions overlap, you can make a file as your second partition that is actually contained on the first partition. And that's completely legal if the checks are skipped around. By fingerprinting the host, you can also identify what sort of machine is using your disk. So say that I'm not really worried about criminal investigation, because all of my research is public and I know that I suck at crime. But I am worried that I might, say, drop a thumb drive that someone else might pick up. Say one of you, okay? But I know what operating systems I use. And say that this disk is only going to be used by me personally and I don't intend to pass it around. Well, I, for example, am using Debian without an auto mounter or a graphical file manager. So that's a very specific thing to fingerprint. Because when you plug a thumb drive into another machine, if I see the master boot record being read 9 times, it's probably not my laptop. If I see like a .ds store directory being written, it's probably not my laptop. If I see that the file system is crawled within 1 millisecond of the disk being inserted, well, I'm pretty sure I can't type that fast. So it's probably not my laptop. When I see a file being written, overwritten, and the new file is the same size as the old one, does it get written to the same place? CP in Linux will directly overwrite the old file in the old location on a fat partition. Some of the graphical browsers will actually erase it and then place the new one in at a location that's different from the old location. And so using these tricks, you can identify what the host is and then destroy yourself if it's the wrong one, or perhaps present a wrong image until a very complicated recovery process has gone through. So the way that delete works is that your 8.3 file name is actually 2 separate fields. So even though you see it with the period in the middle, the period is not part of the file name. The 8 part and the 3 part are physically separate in the structure, and the 8 part is the part that's considered the name in the file system standard. So to delete a file, you just mark the first byte as a 0. So if these are the bytes of the file name, you just 0 the first one, and then the file is deleted. That's all that it is done. And this is why all the subsequent metadata and data are left around. The long file name survives, the blocks themselves survive, and that can all be recovered. And because these thumb drives are loaned out, this can be recovered. And the tools for recovering this include undelete.exe, which shipped on DOS 5.2 and still works on a modern thumb drive. And the disk can fix this by zeroing these file blocks when it sees that they're coming up. And this is kind of like vasectomy security in that you can fix it at one point and it applies to all machines that it gets plugged into. And it shouldn't break any file system drivers because they're never supposed to read the file after they delete it. At worst, you'll break the undelete behavior, which is what you wanted to get rid of. This is also less tricky to compose than the time of check to time of use attacks, because it doesn't really matter in what order or with what purpose the computer is intending to do these accesses. So you can fix all sorts of bugs that exist in the host operating system, but that for some reason have been left around since DOS, in the disk itself and without having to modify the host's behavior. So instead of having to fix these file system drivers on every modern operating system, you can just fix it on the thumb drive and it follows you wherever you go. To trap on imaging, the first step in the criminal forensics lab is that they image it and they record the checksum so that on the stand in front of the judge and jury, the forensics expert can say, I know that this is the disk that I got because I took the image and it was this checksum, and everything here is just as it was when it was handed to me. But the disk can detect it and nuke its own contents. First, by block order. So legitimate access follows the file system structure. But imaging is linear, and the accesses are a lot larger. And they also cross file boundaries. So in a regular fat file system, you will never see two files being read in the same access. When imaging, you will, and even if you randomize the order in which the blocks are requested, you're still going to violate this rule unless you crawl the file system, which will leave things out. This is how legitimate access works. I'm not sure how well the focus is, but I hope you can read a few of the numbers. At least you can see by their width that they're changing rather dramatically. And that's because this is bouncing to the end of the file system and then moving back. The particular image that these screenshots are from is the FreeDOS 1.1 source code CD. When you read a file, the directory entries which are cached include the file's logical block address and the file's length. And that's how it's fetched. So this being a log of fetches that were made by the operating system to my virtual disk, the final record says that 28 blocks at logical block address 280 were requested when I told the host operating system to cat MNT setup. And that's because in FAT, all of your files are contiguous. They're never split up. And so for smaller files, they get accessed in a single record. If this doesn't line up with where the file boundaries are, you're probably being subject to something funny. Now, in DD, you've got the block size parameter. And before starting this project, I thought that the block size parameter would describe how many bytes would be made in each request. But it's not. It's purely for arithmetic reasons. So what happens is that the host operating system will actually group these requests together. And you can see that it keeps trying to increase the number of blocks that are read. And also, you see that they're being read in linear order. It reads 0 first, then 32, then 276, then 280, then 312, then 376, then 504. It's trying to jump ahead as fast as it can. And this never happens during legitimate usage, because a lot of this is empty space before the first partition. So to trap on imaging, you look for sequential access starting at block 0, and you look for block requests that are in a linear order. And you look for chunks of blocks that contain multiple files. And these three rules give you almost perfect recognition of whether or not your disk is being imaged. You can trap on the timestamp, which Windows writes, in order to distinguish between a regular Windows machine and a regular Windows machine with a write blocker. In a bit, I'll get to a fancier trick for finding a write blocker. You can also do host fingerprinting. So Windows writes timestamps. This timestamp is only done by Windows and is easy to identify. Windows also reads the master boot record 9 times. No one else has replicated that bug, so no one else reads it 9 times. A Mac can be easily identified by the set feature command in USB, which a Mac will use during initialization. Every other operating system waits until this command is necessary before using it. FreeBSD speaks a very antiquated, old-timey dialect. So it reminds the disk to turn caching on just in case the disk forgot. and no one else does that. OpenBSD can be identified because it doesn't stall on USB errors. It has a much faster timeout than the other operating systems. So if I have a bug in my enumeration code, Linux will wait 2 seconds before it finishes enumerating. OpenBSD finishes in a number of milliseconds because it doesn't delay on these bad commands. And that perfectly distinguishes the two. Now, Linux distributions can be distinguished from each other because if you've got, say, an exploit for the host, you want to make sure that you're using the right version. You want to know whether the host is 32-bit or 64-bit. You want to know which window manager is being used, which the rest. And you can find this out because each Linux distribution tries to distinguish itself by having a fancier window manager and a fancier file manager. And the file managers all behave distinctly. And the auto mounters all behave distinctly. And all of this runs over this SCSI bus through USB, so you can observe all of this and fingerprint on it yourself to have the right attack for the host. Now for write blockers, so they act as a SCSI packet filter, or basically a firewall, right? And you know, when you've got your introductory book on firewalls, the first thing it tells you is that it's best to deny everything and then allow only those things that you need. So they read that book and they do it. So the bug in this is that, you remember how I said that Linux first says, hey, wouldn't you rather speak ATA? Well, that gets chopped out by the firewall. So if you're ever being used by a Linux machine that does not ask to switch over to ATA, then you're being used through a write blocker. And that allows you to identify the write blocker and then nuke yourself and destroy any evidence that might be left over. So the next steps of this will be to do standalone hardware, both as like a development board that you can work on and poke things, but for this to really be effective, it needs to be Hello Kitty. Because any forensics lab in the world, if it sees a Hello Kitty thumb drive, will immediately shove it into the disk imager. Right? If instead you had, you know, like Bob's super secret tamper-proofing anti-forensics disk labeled on the side, then they might know to not destroy the evidence. And the thing here is that as long as the forensics guy doesn't realize that the disk is special before he sticks it in the machine and pushes the button, you've won. It's game over and he can't win. Because that old rule about the attacker always winning relies upon the attacker having enough chances or enough tries. And here you can make a single failed attempt enough to call the game for the defender and to destroy any evidence that might be left over and replace it with goatsies. We also need to write more time of check to time of use attacks. Colin wrote it for the Samsung TV, but the Samsung TV is certainly not the only one that's vulnerable. How many shell scripts do you know that read a file first in a test and then do something with it afterward? Or ever read something twice from the disk? Well, those ought to be exploitable. You know, perhaps when a machine is booting a kernel off of a thumb drive, it first checks the signature and then it reads it into memory. If that's the case, then you've got an exploitable target. And if no kernel has yet been loaded, then it's quite likely that they've not implemented a cache, kind of like Windows. You can also do, we also need more SCSI utilities because we need to be able to figure out the behaviors of real disks and bugs in real disks in order to start attacking them. Because in the same way that the disk can attack the host can attack the disk. And this needs to be investigated. In particular, we need cache flushing bugs. Because if you recall that Colin needed a 300 megabyte file, and if you also recall that the face dancer is a bit slow, 300 megabytes takes a long time to send over a serial port, such as the FTDI chip inside of the face dancer. So there are other cache flushing bugs that you can come up with. In particular, I found that if you cause a timeout in the middle of a directory request with the VFAT driver, a timeout, not an error, just a timeout. Then the second time it requests the directory, it will have flushed the buffer. And this allows you to effectively disable the file system cache And then you can have a very small file, or a file of which you don't control the size, be reread without the cache interfering. So please read the fucking papers. I would appreciate it. And at this point, I think we have 5 to 10 minutes for questions.
Thank you, Travis. We will be taking questions at microphones 1, 3, 4, and 2, or on IRC. Do we have any questions from the Signal Angel? One question. Do you have a microphone? Fire away.
Okay, thank you very much. The first question actually was, is Sergey at 29th Congress? And if so, can somebody teach him? And if so, would a workshop be better than one-on-one session?
Sergey is at the Congress. He's trying to hide, but he's being pointed out over there. And I think that one-on-one lessons might be better than a workshop. But perhaps we should have a workshop today that then does a series of one-on-one lessons tomorrow to maximize the amount of Gagnam that we can teach him.
Next question will be from microphone number 1.
Okay, this is a sort of twofold question. The first one is, how fast are you on the UART on your board, roughly?
At the moment, we're running at 128 kilobaud. You can run it faster than that, and a subsequent version will be doing USB directly on both sides.
Oh, okay, because FTDI can run plenty fast, actually.
Yeah, the speed issue is temporary because we've been lazy at refactoring our design.
Okay, I sort of recognize that why you wanted to have a device with 2 USB connectors, to have your regular PC, etc. But still, embedded devices can be also plenty easily controlled, and there are gadget drivers, etc. Was there a specific reason why you didn't go that way?
So we looked at the gadget framework. But we couldn't find a machine that both had gadget support and its own host port that was easily available and cheap. So these we can pump out for $10 a piece. Whereas, if you've got to buy a $200 development kit, that drastically reduces the number of devices you can be experimenting with at any given time.
BeagleBone, $90-something.
Cool.
Yeah. Thank you.
Thanks.
Number 2.
When you just want to prevent that somebody forensically images your USB disk, couldn't you also do some sort of SCSI port knocking? So you just write a shell script, so hook it to a UDIF or whatever mounts your disk, that whenever you mount your USB disk on your computer, it first reads the blocks 22 and 42 in that order, and when this doesn't happen, the disk just gobbles up zeros or random stuff?
Yeah, of course you can do that. And by using SG3 utils, you can do that without having to write any custom software on the host that's not already available in Debian. So that will certainly be helpful. Next question.
Do we have a question from IRC?
What sort of host-side protections can be used against those sorts of fuzzing attacks aimed at the host?
You cannot ship with every driver ever written for your kernel. So Chrome OS does this in a way. They include support for a number of USB devices that they expect you to use, but they don't include support for devices that they consider irrelevant or have no host support for. In most distributions, these come from the modules directory, so like /lib/modules and then your kernel version. You can just list the modules that are presently loaded and delete the others. And then you don't need to worry about any random device driver being loaded. But at the same time, these sorts of exploits haven't yet been seen in quantity in the wild. So it might not be something that your grandmother needs to worry about.
Question from microphone number 3.
How does the auto-deletion feature behave in the face of check disk or similar features, tools?
On FAT or in general?
In general.
So that shouldn't cause any trouble. I don't believe that check disk does checksumming out of deleted files or sectors.
Ah, okay.
Question from number 4.
Is it on? Oh, yeah. I just wanted to know if you have any experience with other device drivers than like printer drivers, stuff like that. Have you been playing around with that?
Yeah, so in the source code repository, you'll also find emulators for the USB device firmware update protocol. We've not yet done the printer standards. Perhaps Ang Choi bothered with that and has some notes he could share.
And where can I find you to get one if you need devices?
You can look for the hair.
Okay.
I have got nearly 100 left, so they should last for an hour or two. You could also find Sergey and offer to teach him Gangnam Style in exchange for a board.
Number 3.
Related to the anti-forensics thing, wouldn't it be possible to just like desolder the actual flash from the USB storage device every time you're analyzing one? So you can actually access that with a control chip you made.
So you can do this, and you'll note that a lot of the encrypted thumb drives, as a defense measure against it, just make it absolutely horrific to solder, because they do a system-on-package device in which both the controller and the flash chip are in the same chip packaging. And in order to separate them, you've got to strip the lid with nitric acid, rip the bonding wires, and then rebond it into a new package, which involves considerable labor. You also have the case that with labor being that expensive, require wiring, bonding, and the chemical lab and that sort of stuff, it's impossible to work through a large backlog of disks in that way, especially if 999 times out of 1,000, simply imaging the disk will get you accurate results. So it's a method that can work, but the cost will rarely be justified, at least in criminal forensics. It's possible that if the data on the disk were particularly valuable, and if the forensics guy knew that the disk had a tamper-proofing feature, that it would be worth doing the wire bonding and the rest. So, thank you.
Thank you.
Next question from microphone number 2.
Really interesting talk, thanks. You mentioned that a single block request that spans multiple files is a sign of of imaging or something suspicious happening.
In FAT.
In FAT, perhaps that is what I missed, because I think that the block layer will coalesce requests if I have multi-threaded access to multiple files that happen to land on adjacent LBAs.
Yes, it might. It would still be aligned to their beginning and ends, and I've not yet witnessed that behavior in the VFAT driver of Linux. But you do need to do significant quality control when you're writing something that self-destructs. The manufacturers of the Hindenburg should take note. Too soon?
Okay. Next question from microphone number 3.
Hi. You mentioned that it's pretty easy to fuzz the drivers on the host, especially on Linux, and perhaps Linux distributions shouldn't ship pretty much every driver for USB ever written. I wanted to mention that starting at Linux 3.1, there's sort of a USB firewall. You can decide to not authorize any new USB devices unless they are explicitly marked as authorized. It's the authorized default parameter. And you can use that to disable any new USB devices.
Does any present distribution ship with this enabled? Or?
You can just set it as it's a parameter in /proc, so you can just set it with sysctl. And it should work on pretty much every distribution shipping 3.1 or newer.
I'll try that.
Okay, thank you.
Thank you. IRC?
What would be a good countermeasure concerning a forensic person to counter such a prepared drive?
Given the drive, it would be to get code execution inside of the drive and then have something that would dump out the memory directly. You would preferably already have a sample or several samples of the disk that were your own and that you could tamper and break without being penalized. If you only had a single sample, you would be in a terribly difficult situation. In either case, it's not something that you would expect anyone who directly works in like day-to-day forensics to be interested in or to have the capabilities to do. And anyone who does have the capabilities to write a code execution exploit to dump out the memory in the raw, you wouldn't expect to have the time to do that on any given sample, or to be able to do that on a unique sample. So if you were trying to, say, commercialize this idea, you would need to keep the quantity of units sold rather small, or you would need to separate it out into different quality classes, each of which had different and uniquely written code.
Okay, we're going to take 2 more questions, and then we have to enter the room because we will have the Russian thing. The next talk will be up in 15 minutes. But let's just go with 4 and 3 and then end it. I'm sorry.
So how difficult would it be to modify a commercial storage device in order to implement some of these features?
Perhaps wait until my next paper.
Fair enough.
Yeah, some devices do cryptographically verify their firmware, but others do not. And in each case, you're back to just the difficulty of getting the firmware dump, actually composing the new firmware or the firmware patch, and then installing it. And in disks with no protections against that, it's not terribly more difficult than reverse engineering any other software.
Thanks.
Okay. Just go. Last one from number 4.
Okay, excellent talk, but I think you have omitted questions which are not your advantage, because I think destroying the evidence is totally impossible. You can never achieve it in practice because large block reading is obviously very fast and it's visible to a human investigator. Why, for example, if you have random reading, it's already slower. If you have random writing, it's slower. And if you are writing on used blocks, it can be hundreds of times slower, and also uses lots of energy. So I think everybody will just detect that your disk is trying to destroy itself and disconnect it.
You could also make it appear to have destroyed itself, and as long as you're quick about it. For example, on a magnetic disk, there's a table internally of damaged sectors. And by swapping out that table, or just swapping out the start address of that table, you can instantly change the view of the entire disk from one image to another. Or in Flash, if you have twice the flash capacity as advertised, you can switch to the other half and then slowly erase in the background. I'm also relying on the attacker not knowing that this feature is there, which is a vulnerability of this, but one that I still expect to be a significant pain in the neck of the forensics team investigating the disk. So, all right, well, thank you kindly.
Thank you, Travis. Give a warm applause.